In this next homework problem, number 5, out of the DAC set, we give you that it's a 4-bit D-to-A converter, and I give you the input-output. So there's the codes 0 through 111, and then this is the actual voltage output. So it starts at 0 and goes up in this case to 9.7 volts. So gee, it looks sort of like a typical 0 to 10 volt sort of DAC with a 10 volt reference, and we want to see now if this were a real DAC, this is what we might measure, and how good is this DAC? How can we see if it's meeting its specifications or not? So the first question is the output monotonic, one tone, one direction, one slope? So if we look at it, we can just, something I'm going to want to do is plot this, but before I do that, I might just look at it by eye and say it goes up, it goes up, it goes up, and I'm expecting as the code increases here, I've got more or less a logic truth table. 0, 6, 1.2, 1.8, 3.2, 3.8, 4.4, 5.0, 4.7. Wait a minute now. That went up to 5 and down to 4.7. So that seems a bit non-monotonic. Back up to 5.3, 5.9, 6, 7, 8, 9, 9. Okay, so it looks okay, except right in here, I see that it gets up to 5.0 and then drops down to 4.7. So that, if I was plotting this, and I'm going to, it's got this up, 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 down, up, which is not what I expect, and which can give me a lot of problems if I'm expecting the curve to go one way and it suddenly reverses. So that could get me in trouble. Okay, and looking where it happens where, let's see, 5.0, 4.7. So it happens when I go from 0, 1, 1, 1 to 1, 0, 0, 0. So this is one of these cases where all 4 bits are flipping from the bottom 3 being on and the top one being off to the top one being on and the bottom 3 being off. So, gee, it sort of looks like maybe this is happening when I finally turn on this 1 in the most significant bit. Could be, and that might be the easy answer to which bit is causing the problem. Okay, but let's take a look at a couple of things. Before I plot this even, I can see the effect of each individual bit if I look at the point in the table where only that bit is on. So for example, for the LSB, I can say if it's the only one on, I get 0.6 volts out. And I guess I need to point out that if I put in all zeros, there's 0 coming out. So as far as a pure offset, it doesn't look like this thing has any constant offset that's shifting the whole curve any one way. So I can see that when the LSB is on, it's got a value of 0.6 volts. Okay, and then when I go up and only the second least significant bit is on, which would be here, then I get 1.2. So gee, that's sort of taking the trend I want. This has one value and this has twice as big. I'm expecting this 1 bit here, therefore should be 4 times as big as the other. So it turns on and I get out a 3.2. That gives me some pause because 0, 0.6, 1.2, I would expect it to double again once I get and turn that, if you call it the 1s, the 2s, and the 4 bit on. And it's 3.2. So it's doing the right thing, it's getting bigger as I introduce each bit, but that's pretty far off from where I'd expect it to be. So what I see here is, let's keep going and look at the 1s, 2s, 4s. 8-bit is, when it's the only one, I get 4.7. Well, that doesn't sound like exactly 8 times as big as my 1 bit either, although it is pretty close. 8 times 0.6 would be 4.8. Okay, so we'll come back to that, but let's, I'd maybe expect you to think that plotting this would be a good idea, and it is, because then you get a picture of what does the curve look like. Okay, so just take those same values. I'm going to input across the code, and what I see is starting at 0, 0, 0, I get a 0 out, and then it steps up by 0.6, then it steps up 0.6 again, because this is where the second bit is on, and it steps up by 0.6 again, because that's when both of these are on, and then it takes a big jump here, because that's when my, let's see, that's the first time my 0, my 4-bit, my 4 times as big valued bit clicks in, and it jumps up a bunch. And then it continues on, then I add 0.6, then I add 1.2, then I add 1.8, and then here's where I recognize the non-monotonic aspect of it, because I'm turning off all 3 of the lower significant bits, and I'm turning back on my turning on for the first time my most significant bit. And I see the output value drops from, what was it in the table, 5.0 down to 4.7. Okay, and then it continues on. I'm adding in the LSB and then the LSB plus 1 and then both of them. And then again, I hit this 4-bit and it jumps up again. And then it takes on okay. All right, so whereas we see that this is where the problem in non-monotonicity occurs, we really recognize that it's the 1, 2, it's the 4-bit, the 4 times as much as the LSB valued bit. When it turns on, I get a big jump up, and when it turns off, I get a big jump down. And then it turns on again, I get a big jump up, and if I kept going, I'd see another big jump down at the end of all this. So looking at the shape, you know, there's a little bit of contribution from the fact that the number 8 bit is not quite as big as it should be, but that's a relatively small error as far as the differential noise nonlinearity. Okay, so coming back here again, if I look at this, what I'm going to recognize is, looking at these values, I really get that my LSB seems to be working pretty well at 0.6 volts. And my 2 times LSB is working pretty well at 1.2 volts. And both of those are working just great. But my 4 times LSB, I'm expecting 0.6 here, I'm expecting 1.2 here, I'm expecting twice that would be 2.4 volts there. I'm expecting 2.4, but it turns out to be 3.2. So its contribution is 3.2. I get up to 8 times LSB, and I'm expecting 8 times that would be, I'm expecting 4.8. So expect actual. Okay, so, and it is 4.7. So if I look at what my bit error, or maybe, yeah, whatever, we'll call it bit error. In other words, if I flip on that bit, and that's my LSB, that's my twice LSB, that's my 4SB, whatever we're going to name these, A, B, C, D in this case, this is A, B, C, D. So my bit error in this case, well, looks like it's going to be 0 because I'm basing everything around what is my LSB. And I got 0 for this because that's exactly twice that. And now this one I'm expecting 2.4, but I get out 3.2, which is my bit error is 0.8 volts, right, is the difference between what I expect and what I've got. And that is also, I guess we can recognize that is greater than 1 LSB. And that is the test for, are we going to be non-monotonic or not? I think I said in class at one point if it was greater than 1/2 LSB, but it should be, if it's greater than 1 LSB, you will definitely have a non-monotonic output. Then we get back to here and we expect 4.8, we get 4.7, that's 0.1 volt, and it's less than 1 LSB. So this bit B, the second most significant bit, is actually the one that's causing us the problem. And that's why, you know, we see it show up in this plot. You can see that, you know, how many times do you see what looks like a pretty strong discontinuity? It happens once, twice, and up. So this goes back to the counting cycles kind of thing. I said that if it shifts once, then you're going to see that it's the most significant bit. You know, across the whole full scale range, if you only see one shift, what would that look like? So if we were seeing that across the whole full scale range, we might see something like, you know, some sort of line, and then it shifts. And it might shift down, it might shift up, but as long as it only shifted one time, then we would recognize this as being the LSB, excuse me, the MSB, the most significant bit. What we're seeing here, you know, it shifts up, shifts down, or actually, yeah, shifts up, shifts down, shifts up. If we kept going, it would shift down again. Now the converse of this, because you know we recognize it's happening with a second most significant bit. Here's another case where instead of being too large, like in the case we saw here, our 4-bit, or four times as big as the LSB bit, or B bit. Here it's smaller, so it shifts down, then up, then down, and so you can see more strongly the non-monotonicity when this thing kicks in. And of course it could be more complicated where you have a significant amount of shift from more than one bit, and then they can combine and actually cause you know, different wave patterns across the whole thing. With these real simple you know, 3 and 4 bit DACs, you're not going to get that much variation. Alright, anyway, so what we're looking for here as a solution is that it is non-monotonic. So is the output monotonic? The answer is no. And second of all, it's the B bit that causes the problem. So, enlightenment.